Now, before we go into detail of the Pascal's triangle, I just want to make sure that you know that the Pascal's triangle is really just an introduction into the binomial theorem. So in no way is it just the binomial theorem, okay? So just think of it, it's an introduction to it. And although it's a simple method, it's a very limited method for expansion. All right, now, first things first, what exactly is the Pascal's triangle? So I'm sure that we've kind of heard of this term before, but let's revise exactly what it is. Now, the Pascal's triangle is really just a sequence of numbers, but the only difference with that is that it starts off with two numbers, unlike normal sequences, right? So it's starting off with two numbers, 1 and 1. And then to get the next few numbers, this is what we do. So the first number is always going to be 1, yeah? And the last number is always going to be 1. But the number in between them, we get from the addition of the previous numbers. So to get this number, we add 1 and 1, yeah? And that gives us 2. So this here has 1, 2, 1. All right, so let's find out the next series of numbers. So remember, always starts off with 1 and it always ends with 1. And to find the numbers in the middle, we add together 1 and 2. So that should give us 3, right? And add together 2 and 1. So that should give us 3 as well. Yeah? And now can you kind of see how it forms that triangle shape? And that's why we call it the Pascal's triangle. So using this method, you can see how we can kind of keep going forever. So it always starts off with 1. And this number here would just be 1 plus 3, so it'll give us 4. 3 plus 3 will give us 6. That'll give us 4, and we'll end off with 1 as well, and so on, yeah? So as long as you know the basics for that, you can work out the Pascal's triangle. But you can also see how frustrating it's going to be if you want to go to 20 or 50 or something. You'll be sitting in the exam drawing forever. So this is why I said it's quite limited, because there's only so many amount that you can do before it's just not worth it. All right, so why are we learning about the Pascal's triangle? Well, the Pascal's triangle can actually be used for expansion, all right? And I'm going to show you how. So firstly, let's consider the first set of numbers in the Pascal's triangle. So that's 1 and 1. And the Pascal's triangle are actually used as coefficients for expansion, yeah? So just remember, these are going to be coefficients. So this may be a bit confusing now, but I'll show you how it works. So to start off with, let's have a look at the expansion of a plus b to the power of 1. So this is how we do it. We think about the fact that we start off with number 0 and then we increase to 1 and 2 and so on. Yeah? So just keep that in mind. Now, we have A and B here. A is always to the power of that index there. So if that index is 1, it's A to the power of 1. And B, or the second term, is always starting off to the power of 0. Yeah? So it starts off with 0. Now, to go on to the next term, you subtract 1 from A's index and you add 1 to B's index. So this becomes A to the power of 0 and this becomes B to the power of 1, like that. Yeah? And whenever you see that B's index here is the same as that index there, you know you stop. As well as we can't keep going because these indices added together has to equal that one, yeah? So a couple of notes. The first thing is we always start off with 0 there, okay? A is to the index of the same as that, and you end when B's index is the same as that, yeah? And you can kind of see how because we're starting off with 0, we're going to have 2 terms here. So when you have to the power of 1, you get 2 terms. Just keep that in mind. Now, let's go back to the Pascal's triangle and the coefficients. So how does this fit into here? Well, this 1 and 1 become the coefficients of this expansion. So 1 goes in front of the first term and that 1 goes in front of the second term, just like that. And all you need to do now is simplify. So that just becomes a times b to the power of 0 just equals to 1. And here you have a to the power of 0, which just equals to 1 times b. So you get a plus b as your expansion. All right, so this may kind of seem like a overcomplicated way to expand this, but this is just a method that we're trying to learn here. So let's remember, this is how we did it for a plus b to the power of 1. Now let's have a look at the next line in Pascal's triangle. So remember, we start off with 1, yeah? And the next term we get from adding these numbers together, so that's going to be 2, good, and then 1 again. So this is our second line. And this is used as a coefficients for expanding a plus b to the power of 2 there. All right? Now, we use the same method. So remember, a is going to be to the power of the same as that. So it'll be a to the power of 2. And b, you always start off with b to the power of 0 there. And now what do? Yeah, that's right. So just subtract 1 from that index and add 1 to that. So that becomes a to the power of 1, b to the power of 1. And again, subtract 1 from that, add 1 to that one there. So you get 0 and 2. And remember, when b, or the second term, has the same index as that, right, we stop. As well as you see that if you do keep going, these indices won't add together to equal 2. Okay? So remember, these indices always has to add together to be the same as that index there. Now we use the coefficients from the Pascal's triangle. So it's really easy. The first number there is a coefficient for the first term. The second number is a coefficient for the second term. Third number is a coefficient for the third term. Yeah? So super easy, just put it straight in there. And now simplify. So this just becomes a squared, yeah? 2 times a times b. And that just becomes 1, so you get b squared. And this, as we're familiar with, is indeed the expansion for that, yeah? Okay, good. So this is for power of 1 and power of 2. Now, let's have a look at the next line, okay? So start off with 1. This term is going to be 1 plus 2, gives us 3. 2 plus 1 gives us 3 as well, and then 1 there. Now, this is a little trick that you can use. This diagonal that you see here, so kind of the second diagonal of the Pascal's triangle, tells you which line to use for your expansions. So if it's to the power of 3, you know to use this line because you look for the 3 there, yeah? And if it's to the power of 2, like before, look for that 2 there, so you know to use this line. And it's quite good when later on you get up to higher numbers. So if you see power of 7, you don't need to count down all the way to 7. You can just see, yep, 7 is the second number there. That's the line that I'm going to use. Okay, let's expand this now. So the first term is going to be, that's right, a to the power of 3, b to the power of 0. Subtract 1, add 1. So that becomes 2 and 1. And subtract 1, add 1, 1, 2. Then finally, subtract 1 from that, becomes 0, add 1, becomes 3. You can see we have power of 3 on our second term, which is the same as that index there, so we know to stop. Now remember how I told you to remember when we did the first one, that when it was to the power of 1, we had 2 terms because we started off with 0. And when we had to the power of 2, we had 3 terms, once again because we're starting off with that 0. And now you can see that when we have the power of 3, we have 1, 2, 3, 4 terms. Yeah? Can you see how there's a pattern evolving? So how many terms do you think we would have for the power of 4? Exactly, 5. And for power of 5? Good, there'll be 6 terms. So there'll all be 1 more term than the power there. And you can kind of see how the Pascal's triangle fits perfectly with that. Because for the power of 3 here, you can see there's 4 coefficients for 4 terms. Just as for the power of 2, there's 3 coefficients for 3 terms. Yeah, can you see how there's that pattern? All right, so let's just put in our coefficients. So remember how I said really easy. First one goes there, that 3 goes to the second term, 3 to the third term, 1 to the fourth term. Super easy. And now just simplify. That's a cubed, 3a squared b, that becomes 3ab squared, that just becomes 1, so you get b to the power of 3. And once you're fully simplified, that is going to be the expansion of a plus b to the power of 3. All right, great. So let's go on and have a look at the fourth line here. So for this one, let's work out what this series is going to be. So 1 plus 3 gives us 4, right? 3 plus 3 gives us 6, good. 3 plus 1 gives us 4 again, and that ends off with 1, okay? And if we extend this diagonal, you can see that this is going to be for the power of 4, right? And there's 1, 2, 3, 4, 5 terms, yeah? So it's following that pattern. All right, so let's expand that. We know it's going to start off with a to the power of 4, b to the power of 0, yeah? And then you'll become 3, 1, and this will become 2, 2. Next one will become, yep, good, 1 and 3 there, yeah? It's going to end with a to the power of 0, b to the power of 4, yeah? So easy there. And now we put in coefficients. 1, 4, 6, 4, 1. All right, and now we simplify. So this just becomes a to the power of 4, 4 times that, 6 times that, 4 times that, and finally, because that just becomes 1, that's just b to the power of 4. And this is going to be your expansion for a plus b to the power of 4 there. Yeah? Okay, so let's go on to a question now. So I want you to remember how to expand that, and how the most important thing is the Pascal's triangle is to give us the coefficients. And you can see how useful it is to expand a plus b to the power of 4, which usually you'd have to write separately and expand, and it all become too complicated. Now, in question 1 here, we want to draw the Pascal's triangle and then expand for a plus b to the power of 5. All right, so we didn't do that in the example, did we? We kind of stopped at a plus b to the power of 4. So let's first draw our triangle. So it's 1, 1. The next one is 1. This term's going to be, yep, 2. Always ends with 1. Starts with 1 again. This will be 3. Good. Yep, 3, 1. Next line, 1. This one, 4, 6, 4, 1. Excellent. Now, what's the fifth line going to be? Starts off with 1, that will be 5, 10, yep, 10, 5, and 1. Exactly. So you can see that for the power of 5, there's going to be 6 terms altogether. All right. So what we need to do now is expand that. So remember, we kind of have 3 steps. First step is to expand that. Second step is to put in the coefficients. And the third step was to simplify. So first step, expand that. So we start off with a to the power of 5, b to the power of 0. And we know we're going to end with a to the power of 0, b to the power of 5. So all you need to do is fill in the ones between. Subtract 1, add 1, 4, 1. Subtract 1 from that, add 1 to that, a to the power of 3, b to the power of 2. Subtract 1, add 1, 2, 3, that becomes 1, 4, and we finish with a to the power of 0, b to the power of 5 there. All right, good. And the second step was, excellent, yeah, just put in the coefficients. So super simple. 1 goes there, 5, 10, 10, 5, 1. And then lastly, simplify it. So that just becomes a to the power of 5, right? And this will just become b to the power of 5. And really that itself is already quite simplified. And just rewrite it out, simplified, and leave it as that. And you've just done the expansion for a plus b to the power of 5. Yeah? In really what was only 2 lines, which is much, much easier than trying to expand this any other way. Okay, good. So this was for a plus b to the power of 5. Now, let's have a look when we have a negative there instead of a plus. So have you noticed how all the expansions we've been doing has been a plus b? So how do you think we're going to do this expansion if it's negative b? So have a think how we might do that. Well, let's just start off with, this is going to be our coefficients, right? So 1, 1, 1, 2, 1. This will just be 1, 3, 3, 1. Okay, we know we'll be using this line. Now, what we do is we just think about the negative b as the second term. Yeah, so it's still the first term plus the second term. It's just that in this case, the second term is negative b. All right, and that's kind of how you do any changes in this. So although we've been talking about it as a plus b, you should kind of think about it as a first term plus the second term. Yeah, so our first term here is a, our second term is minus b. All right, so this means that when we expand it, the first term here is just going to be a to the power of 3 and then negative b to the power of 0, like that. Yeah, and then exactly the same. Subtract 1, add 1. So a to the power of 2, negative b to the power of 1. Same thing, a to the power of 1, negative b to the power of 2. A to the power of 0, negative b to the power of 3. Now exactly the same, once that second term, so negative b, has the power of 3, which is the same as that index there, we stop. All right? So can you see how it's exactly the same except that instead of having b, we just have negative b as our second term. Now, second step is to put in our coefficients. So 1, 3, 3, and 1. And now, just to simplify. So here, we've just taken a few more steps in simplifying it. So this one just becomes 1, yeah? So that becomes a to the power of 3. Negative b to the power of 1 remains negative b. Whereas negative b squared, that squared gets rid of the negative, so it just becomes b squared. And this just becomes negative b cubed, yeah? Because negative cubed is still negative. So once you fully expand that, should get a cubed minus this, plus that, and minus b cubed finally. Yeah? Can you see that? So when you have the first and second term is slightly different, it may take a few more steps in simplification, but that is the only difference there is. All right? Okay, good. So that's how we do negatives. Now, let's have a think about what we do if we have 2a or 3a or whatever instead of just a by itself. Okay, first thing is it's power of 3. So let's work out our Pascal's triangle. So 1, 1, 1, 2, 1. We should know this pretty well by now. 1, 3, 3, 1. And that's what we're going to use. So to expand this, we use the same thing that I taught you before, which is that this is going to be our first term. And this is going to be our second one. Yeah? So instead of just having a to the power of 3, b to the power of 0, I'm going to be having 2a to the power of 3, b to the power of 0. Yeah? Subtract 1, add 1. 2a to the power of 2, b to the power of 1. Subtract 1, add 1. 2a to the power of 1, b to the power of 2. And then finally, we have b to the power of 3 there, so we know we stop. All right? And then coefficients, good. So 1, 3, 3, 1. And now we need to simplify that. So I think the easiest way to simplify this is let's just expand these brackets first. So 2 to the power of 3 gives us 8a cubed, b0, but b to the power of 0 is just 1. Here we have 2 squared, which gives us 4, and a squared. 2a to the power of 1 is just 2a, and 2a to the power of 0 is just 1, so that just becomes b cubed there. All right, done that, let's simplify more. So we can just multiply these two numbers in. So you end off with this finally, okay? All right, so exactly the same principles, only difference is that we have 2a here instead of a. And what's really important, because I think this is where a lot of students go wrong, is make sure you put your brackets here. So you have to have bracket, bracket, to the power of 3. Because if you don't and you just write, for example, 2a to the power of 3, right? Can you see how you're going to get yourself confused and forget to make that 2 to the power of 3 and make it 8? Yeah? Because when you're rushing, it's a really easy mistake to make. So remember, for these expansions, brackets are your best friend. All right, great. So this was to expand 2a plus b. Well, how about when we're working with fractions? So it's the same principle, but a little bit more difficult in our simplification, that's all. So Pascal's triangle here is going to be using 1, 3, 3, 1, this line as well. And we're going to expand that. And all we're going to do is take this as our first term and take that as our second. So we'll have a to the power of 3 and brackets, 1 on a to the power of 0. Okay. Next one will be 2 and 1. So once again, these brackets here, important. 1 to the power of 2. And then we have 0, and then we have to the power of 3, so we know we stop. And then put in our coefficients, 1, 3, 3, 1. And now to the bit that's a little bit more difficult, so our expansions. So as previously, I think the easiest thing to do is to just work with the brackets first. So in this bracket, power of 0, it just becomes 1. This, just power of 1, so it remains 1 on a. This is 1 on a squared, so it becomes 1 on a squared there. And that a just becomes cubed, all right? So expand the brackets first and then simplify by multiplying together. So nothing you can do here, but look for what you can cancel. So can you see how that a can cancel with one of those a's? And this a here can cancel with one of those a's, like that. So finally, you should get a to the power of 3, that just becomes 3a times 1 is just 3a. That is 3 times 1 on a, so you just get 3 on a. And finally, that's just 1 on a cubed. Okay, can you see that? And you can just leave that as is, and that's your expansion. So you can see that where people go wrong is really not going to be here, is it? Because we know how to expand this, we know how to put the coefficients in. The mistakes you're going to be making is when we're simplifying it here. And if you just make brackets, expand the brackets first and then simplify everything later, it's the easiest way to make sure you don't make those silly mistakes. All right, let's have a look at question 5 here. So here we want to expand a to the power of 2 plus 2 and to the power of 4. So we're going to be looking at this index first, power of 4. Let's work out Pascal's triangle first. So that's 1, 1, 1, 2, 1, 1, 3, 3, 1. Okay, we haven't done the next line in a little while, so what's it going to be? 1, yep, and that's 4, good. 6, good. 4, and 1, finally. Okay, now to expand this, just think about this is our first term that we're expanding and this is our second one. So we have a squared and that whole thing, brackets, to the power of 4. And this is 2 to the power of 0, all right? Following your same patterns, subtract 1, add 1. So that becomes power of 3, power of 1. Subtract 1, add 1. Power of 2, power of 2. Power of 1, power of 3. And finally, power of 0, power of 4. And that 2 is to the power of 4, which is the same as that index there, so we know that we stop. Great. Put in your coefficients, 1, 4, 6, 4, 1. Okay, let's expand these brackets. So here, remember when we're multiplying the index with brackets, we just multiply them. So 2 times 4 is just 8, 2 times 3 gives us 6, 2 times 2 gives us 4, 2 times 1, 2, and power 0 just means it equals to 1, yeah? So that's how we get to this step here. And now we just do the last step, which is just multiplying these coefficients and numbers together essentially. So that gives us 8, 8 power 6, 4 times this 6 gives us 24, 8 power 4, 4 times 8 gives us 32, and 16 there. And you can actually see with that, you just check it's to the power of 4, and yes, we do have 5 terms there, so it's a good way to check with that.